Assalamualaikum and hi doctors. For today, I'm going to be explaining about groups. Okay. Groups. First of all, my name is Sultan Sulaiman. Okay. For group, definition of groups. In order to prove that the binary structure is a group, you need to prove that it is associative, it have identity element, or it have inverse element. Okay. After you have all that element that you have been proving in the binary structure for, then it is considered as a group. Okay. So now let us continue about the properties of the groups. Okay. The first property is the left and right cancellation law, or known as LCL and RCL. Okay. If the group, this is just like the general operation of the groups. Okay. So let us see that the definition of theorem 1, where it says that when A star B equal to A star C, it means that we can substitute that the B is equal to C. So that's why we will get A star C. Okay. In order to use RCL or LCL, we need to see where is the element that we need to cancel, the position of it. So for this one, it is on the left hand side. So in order to cancel the A in this form, we need to use LCL, and the other one, which is the A, is in the right hand side, so we need to cancel it using RCL. Okay, this is the example. Okay, the next theorem is the next property is unique solution. Okay, if G is a group that have a binary operation star, and if A and B are element of G, then the linear equations A star S equal to B and U star A equal to B. Okay, this is to prove the solution that we get is a unique solution. Okay. This is the example where we just using this is how to prove the existence of unique solutions. So you just take the either A star S or A star U. Then we just need to do we can solve it by using the definition of the group. Either you can use associative, identity, or inverse. It's up to you how you see the solution. Then you will get B for U and S. Okay, this is the way to show that the solution that you get, for example U1 and U2, is a unique solution. Okay. Next is theorem 3, the last properties, which is the uniqueness of identity and inverse element. So as we all know, if the binary structure is a group, then it will have the identity element and the inverse element. So this is the way to prove that the inverse and identity element that you already got is a unique one. Okay. So this is just a simple way to prove the identity. Okay, next, this is the way to show that the inverse element is unique, where we just need to assume two different inverse elements. So by doing that, you will get the properties of the group. So that's all from me. Thank you.
Assalamualaikum and hi doctor. So my name is Siti Norazli binti Faridun. I will explain about ring. Okay, first I will explain about the definition. Next. A ring is a set with two binary operation, addition and multiplication, such that for all A, B, C in R. So from 1 until 6 is a condition that we should follow, so we can call it as a ring. Next. Okay, a ring is an abelian group under addition and also having an associative multiplication that is left and right distributive over addition. Note that multiplication need not to be commutative. When it is, we said that the ring is commutative and a ring need not have an identity under multiplication. explain about the properties of ring. There is 3 properties of ring that I will explain. Okay, first is about rules of multiplication. So rules of multiplication, there is six conditions. The first one is A0 equal to 0 equal to 0A. So this one are the way to prove it. Next. The second condition is A bracket negative B equal to bracket negative A bracket B equal to negative the bigger bracket A B close the bracket, and these are the way how to prove it. And do not assume that multiplication is a commutative. So third condition is bracket negative A close open negative B close the bracket equal to AB. So these are the symbols how to prove it. And the fourth is A bracket B minus C close equal to AB negative AC, and bracket B minus C close A equal to BA minus CA, and these are the way to prove it. So the fifth and sixth. Furthermore, if R has unity element 1, then negative 1 bracket negative 1 close A equal to negative A, and bracket negative A close the bracket open the bracket negative A close the bracket equal to 1. Okay, the second properties, uniqueness of the unity and inverse. If a ring has a unity, it is unique. So this example how to prove that the element is unique. Okay, this the second also, uniqueness of the unity and inverses, said that if a ring element has a multiplicative inverse, it is unique. So this example how to prove multiplication inverse is unique. So these are the last but not least properties about ring is subring test. Subring test say that non-empty subset S of a ring R is a subring if S is closed under subtraction and multiplication. That is, if A minus B and AB are in S whenever A and B are in S. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Idris. I will answer the question for number 2. For today, what is a field? A field is a ring in which the non-zero element form an abelian group under multiplication. In other words, a field is a non-trivial commutative ring R satisfying the following extra axiom. For each non-zero element A in R, there exists A inverse in R such that A dot A inverse equal to A inverse dot A equal to 1. Determine whether R is a field or not. For the first step, we have to show that there is inverse in R under binary operation of addition. To find inverse, we first have to find the additive element of R such that S plus E equal to X equal to E plus X. So we find for the left hand side and right hand side, we get left hand side equal to right hand side. We find the right hand side and right hand side. Then we get left hand side equal to right hand side. Therefore, E equal to 0 in R is the additivity element of R under binary operation of addition. After we get the identity element, we can find the inverse element of R under binary operation of addition, which E as the identity. So we have X plus X inverse equal to E equal to X inverse plus X. So we find for the left hand side and right hand side, we get left hand side equal to right hand side, therefore x inverse equal to negative x over y in R is the binary operation of addition. To show the inverse of R and the binary operation of multiplication is y over x. Do the same step as we do in step 1. We have to find the identity element first. Then we can find the inverse element of R under binary operation of multiplication. Just like the first step, we will get left hand side equal to right hand side, therefore x inverse equal to y in x. Y over x in R is the inverse element of R under binary operation of multiplication. Next step is to show that multiplication is distributive on addition. We have x dot y plus z equal to xy plus z. So we let 3 elements in R and the denominator is not equal to 0. So we find for the left hand side first, then we get is equal to right hand side. So since left hand side is equal to right hand side, therefore the multiplication is distributive on addition. Since we can find the inverse of R under binary operation of addition, we can find inverse of R under binary operation of multiplication, and we can show the multiplication is distributive on addition. So we can conclude that R is a field. For the next question, what is an integral domain? A ring R is called an integral domain if R is commutative, which is AB equal to BA for all AB in R. R is an identity under multiplication. R has no zero divisor and 0 is not equal to 1. For example, let F be a field, show that F is an integral domain. So we let x, y in F, which x dot y equal to 0 and x is not equal to 0. Since F is a field, there exists x inverse in F, since x inverse x is equal to 1, which we have done in previous question. So we have x inverse x dot y equal to 0. Then we get x inverse x y equal to 0, 1 dot y equal to 0, and y equal to 0. So we can prove that F is an integral domain. The last question for my part is, what is the relationship between a field and an integral domain? A finite integral domain is a field. Okay, for example, suppose R is a finite integral domain, show that R is a field. To show R is a field, we have to show all non-zero element in R is unique. So first we have to identify whether so first we let A in R, which A is not equal to 0. So R star is a set of all non-zero elements of R. Suppose that phi is R star implies R star by phi x equal to AX. We want first to show the phi is 1 to 1. So let phi x equal to phi y, which x and y in R. So we have phi x equal to AX. So AX equal to AY. Then AX minus AY equal to 0. AX minus y equal to 0. Since R is an integral domain, we have A equal to 0 or xy equal to 0. But we already know that A is not equal to 0, so we have x minus y equal to 0, which is x is equal to y. Therefore, we can conclude that phi is 1 to 1 and also on 2. Since 1 in R star, there exists x in R. So phi x is equal to y, therefore phi x equal equal to 1, therefore AX is equal to 1. Hence, C is a unit, so we can conclude that R is a field. Assalamualaikum. Okay, I will show you answer number 3. Okay, before I show you the answer for question 3, we need to know the operation of a ring. We have two. First, addition, and second is multiplication. In addition, we have apparent groups and this is below. While the multiplication, we have associative and property. Associative property, and in multiplication, we have commutative or not commutative. It depends on what we choose. We call R is a commutative ring when A dot B is equal to B dot A. And R is a ring with identity when R contains 1 with a identity in S. The differences between units and unity is in units in rings, then R will a ring with identity element of 1 for multiplication. And element R in element of capital R is called a unit on R if there exists S in capital of R for which R times S is equal to 1 and S times R is equal to 1. In this case, R and S are multiplicative inverse for each other. Now we can see the unity, the non-empty ring where it has addition and multiplication is a ring with unity if and only if the semi-groups R and multiplication has an identity element. Okay, such an identity element is known as unity. Okay. Before we need to know that 2 times 2 is a commutative ring, we need to show the property of ring, which is we have additive associativity, additive commutativity, additive identity, additive inverse, right and left law, and lastly multiplicative associativity. Okay, first we need to prove matrices 2 times 2 is a ring. As usual, we prove the R is a closed under additions where we need to let X A1, B1, C1, D1 and Y is A2, B2, C2, D2 where the X and Y is element of sets. Then we add both matrices, then it shows that this element on Z. So matrices 2 times 2 is a closed under addition. So next we need to prove the addition is associative where we need 3 of matrices, anything, and I choose A1, B1, C1, D1, A2, B2, C2, D2, Z and J, B, C2, D3. So we need to prove the left hand side and the right hand side where I get that left hand side is equal to the right hand side. So next we need to prove addition is identity where we know that identity is shown when is 0, 0, 0, 0 in element of Z. So we need to prove left hand side and right hand side. Okay, we need 2 of matrices. I choose A, B, C, D, E, F, G, H, and then in left hand side we assume that E, F, G, H as identity. So we get the identity E is equal to 0, F equal to 0, G is equal to 0, and H equal to 0. While the right hand side, I assume that identity in 5, and then it get the same of the left hand side. So it shows that it's an identity of addition. Next, we need to prove the addition is inverse, where inverse we get from our matrices plus inverse is we can get the identity. So it shows it is an inverse of addition. So next is we need to prove addition is commutative. Commutative where we choose two matrices. So it shows it is an inverse of addition. So next is we need to prove addition is commutative. Commutative where we choose two matrices A1, B1, C1, D1 and A2, B2, C2, D2 where all element in the matrices is element of Z. So we need to prove left hand side and the right hand side. Okay, in the left hand side we add as usual, as right hand side we add as usual, and we get that this is addition is commutative on matrices 2 times 2. So next, under multiplication, before this we see that we prove the addition and next we prove for multiplication. So for multiplication, we need to prove matrices in 2 times 2 is a closed under multiplication. We need to choose two matrices and choose A1, B1, C1, D1 and A2, B2, C2, D2 where X and Y is element of Z. Then we show it that answer is element of Z, and then M2Z is a closed under multiplication. Next, we need to show that multiplication is associative, where we need to choose three matrices, and then we prove left hand side and right hand side. The difference for left hand side and right hand side is the bracket. So we get that left hand side is equal to the right hand side, and we can make a conclusion that multiplication is associative on matrices 2 times 2. Lastly, we need to prove that multiplication is distributive over addition, where we have two laws in distributive. We need to prove left hand side and right hand side. In a matrices is element of Z, and it shows that multiplication is distributive over additions.